Hello there, this is Dr. Armand bringing you another exciting pre-lab video assignment for General Chemistry 1 Laboratories, coming to you out of the Lone Star State. And so in this virtual session, we'll be talking about Lab 4, the reaction involving zinc and iodine. Some of the concepts we'll be touching on in this lab are, for example, calculating empirical / molecular formula is the main concept we're going to use in this experiment. Also limiting an excess or law of conservation of mass as well. And so in this virtual session, we're going to go a little bit background into how do we calculate empirical and molecular formulas, talk a little bit about some of the chemicals that we're using in this experiment, and then some of the key aspects or key points throughout the experiment and what to look for, and then finally showing you a little run through of performing the experiment and doing sample calculations as well. So sit back, relax, and grab your favorite beverage and enjoy the show. So this is lab 4, rocking along the lab series. And so in this lab, we're going to be messing with zinc and iodine. So we're going to do a reaction involving zinc and iodine, and we're going to form zinc iodide as a product. Now, we all know from General Chemistry 1 or General Chemistry lecture that zinc iodide, the actual formula is ZnI2, but we're going to perform an experiment and then determine the formula of zinc iodide based on experimental data. And let's see if that correlates to what it should be. If it is, great job. If it isn't, well, then we need to explain why. So just a little bit about the review on molecular and empirical formulas. If you are taking the lecture, you've already covered this. If you have already completed General Chemistry 1, this will be a good refresher. And so there are 3 types of chemical formulas that we deal with. The empirical formula, which as you can see here contains the smallest or simplest whole number ratio of atoms in the formula. And when you look at the formula, the common multiple between all of them is 1. And the majority of ionic compounds, majority, not all of them, but the majority are written as empirical formulas. So that's one type of formula. The second type of formula is a molecular formula, which shows you the actual number of atoms in that compound. And then the third formula is a structural formula, which those who are taking the lecture course, you'll delve into this when you get to the latter chapters. And this involves Lewis structures. So this shows you the actual bonding of that's occurring in the compound. So just to give you an example of all 3 of these formulas. So we have let's say an empirical formula. We'll say it's, let's see, CH3. The molecular formula C2H6, and the empirical formula would look like this. And I'm free-handing it here, so I apologize if it's a little bit shaky. So these are the 3 different types of chemical formulas. And I wrote empirical twice. Shame on me. So this should be structural. Oops. Not empirical. Now, when we're talking about calculating the empirical formula, there are 3 simple steps. that you need to follow, just like that cartoon where the bear shows them 3 simple steps to complete a task. Anybody know what that bear's cartoon is called? That's right. A special agent OSO. So 3 simple steps to get us to determine the empirical formula of a compound. So in order to calculate the empirical formula of a compound, you usually have to do some type of elemental analysis to get the mass of each element in your compound. This is very important. So once you know the mass of each element in your compound, the next step is you got to convert this to moles of each element. So to go from mass to moles, we need the molar mass. So bam, we got the moles of each element. Then we're going to divide by the smallest number of moles of the smallest number of moles of a particular element. We're going to divide all the other moles by. And this is going to give us a ratio of the elements. And if the ratios are all whole numbers, we can write it as a formula. If the ratio is not a whole number, say 1.5, for example, we're going to have to find some number to multiply by the ratio to get it to a whole number. And so what you have to remember, at least in this lab course and maybe in your lecture course, is the way that the elements are given in the problem is most likely the way you should write the formula, especially in the lab course. Whenever you're given an empirical formula problem, the way the elements are listed in the problem is the way you should write the elements in the formula. So keep that in mind when you're doing the assignments. So let's look at a quick example of this to kind of refresh your mind on empirical formula. Excuse me. So here we have a compound decomposes in a laboratory. We produce 24.5 grams of nitrogen, 70 grams of oxygen. Calculate the empirical formula. So right off the bat, we already have the mass of each element. So bam, we can calculate the moles of each element. That's step 1. Now we use the atomic mass of nitrogen and oxygen. We do not use N2 and O2. This is not stoichiometry. This is empirical formula. So we have to use 14 grams per mole for nitrogen, 16 grams per mole for oxygen. So now we have the moles of each element. We're going to find the ratio by dividing by the smallest number of moles. In this case, it's nitrogen, 1.75. And notice here that 2.5 is not a whole number. And you can't round this to a whole number. This is too far away from a whole number for you to round. And so the obvious question you may ask is, well, how close to a whole number is permissible to round? And my answer to that is it's a gray area. It just depends. Different books may use different ranges. Different professors may use different ranges. But for example, 2.5, 1.25, 1.667, 1.33, all of those you can't round. And so now we need to multiply this, both the moles, the ratio of nitrogen and the ratio of oxygen, or excuse me, yes, to get these as a whole number. And so we multiply it by 2 because it's a half. We get rid of the decimal now. So now we have the empirical formula N2O5, dinitrogen pentaoxide. So again, you take the mass of each element, convert it to moles, divide by the smallest number of smaller or smallest number of moles, get your ratio. If it's whole numbers, you're finished. If it's not whole number, multiply both or all the ratios by some number to get rid of the non-integer ratio. And hopefully this was a refresher on how to calculate empirical formula. Now we're also going to look at molecular formula. So with molecular formula, as I said earlier, it shows the exact number of atoms in a substance. And so here, we have some, usually the common multiple between the elements in the formula is not 1, but it could be 1. Sometimes it is, but most of the time, or I guess a large chunk of the time it's not 1, but it could be. And so how do we find the molecular formula? Well, we just add one extra step to the end of the empirical formula process. So once we calculate the empirical formula, we're going to multiply it by some value n. Typically, n is an integer. I would say the majority of the time. And so this n times the empirical formula gives us our molecular formula. So that's a good question. How do we calculate n? So the way we calculate n, we take the molar mass of the molecular formula. Generally, this is given in the problem. If you're doing a word problem, generally it is given in a word problem. And the molar mass of the empirical formula we calculate once we determine the empirical formula. So we get the ratio of the molar masses, and now we have the n. So just one extra step at the end. So for example, benzene has a molecular mass or molar mass of 78. This should actually be molar. Molar mass of 78 grams per mole. Its empirical formula is CH. So again, from the empirical formula, we get the molar mass of the empirical formula. So now we have the molar mass of the empirical formula, the molar mass of the molecular formula. We can get the value of n and then the molecular formula. So 78 divided by 13 is 6. Therefore, 6 times CH, we get C6H6. So is this n value that you're calculating to determine what to multiply the empirical formula by. So let's look at an example of this as well. So in this example, we have a chloride of silicon contains 79.1% mass of chloride. What is the empirical formula of the chloride if the molar mass is 269 grams per mole? What is the molecular formula? So this problem has two parts. First, we're going to calculate the empirical formula. Second, we're going to calculate the molecular formula. This 269 is the molar mass of the molecular formula. So we're not going to use that yet. We'll use it on when we're calculating the molecular formula. So now we're given percents, and that's not a problem. But remember, this is a chloride of silicon. So what does that mean? So silicon, and this is a chloride of silicon. So since ide, that means it comes second. So this is going to be some silicon, some number of silicon. We'll say X, and some number of chlorides, we'll say Y. Now we know the mass percent of chloride is 79.1%, and there's only two elements in this compound, silicon, or two species, silicon and chloride. So in order, what we need to do is determine the mass percent of silicon. So we can just subtract from 100 and we get the mass percent of silicon. Now here we don't have actual masses of each component, we have percents. And when you're given percents or mass percent of each component, what you want to do is you want to assume 100-gram sample. Now you may say, well, why 100-gram sample? It's very easy to take a percent of 100. You can use any size gram sample you want. It just may be a little bit more not as straightforward to get to percent. So here we're going to have a 100-gram sample. So now we know the mass of chloride, the mass of silicon. Bam. So what's the next step? That's right. We're going to determine the moles of each. Now again, when we find the moles of chloride, we're going to divide by 35.45. We're not using Cl2. So now we got the moles of each element, and this should be chloride here. I apologize. Copy and paste function. So now we got to divide by the smallest number of moles to get the ratio. And here, silicon is the smaller one. And we get that the ratio is 1 to 3. So for every 1 mole of silicon, we have 3 moles of chloride. And we get the empirical formula, SiCl3. Again, silicon comes first because this is a chloride of silicon. So since ide, it means it comes second. We have the formula mass of the empirical formula. We know the molar mass of the molecular formula. We can find the ratio. So 269 divided by 134.44, approximately 2. And then we multiply SiCl3 by 2 to get the molecular formula. So again, with molecular formula, you're just adding one extra step at the end of the empirical formula journey. So again, what do? If we're given percents of mass, we convert it to mass of each element. We find the moles of each element. We divide by the smaller number of moles to get the ratio. If the ratio is whole numbers, bam, we got the empirical formula. We determined the molar mass of the empirical formula. We have the molar mass of the molecular formula. We find the ratio between the two. We multiply it by the empirical formula. Doing the same steps every time. So how does this apply to the lab we're doing involving zinc and iodine? Good question. So we looked at some textbook examples of empirical and molecular formula, but how explicitly does this, how explicitly do we use this in the lab? And that's what we're going to talk about now, the actual calculations you're going to do when performing this or obtaining the data from this experiment. So in this experiment, we're reacting zinc and iodine. So here a student adds 1 gram of zinc metal. That's important. And 1.5 grams of iodine crystals to an Erlenmeyer flask. She then adds 15 mils of methanol to the flask. Then we cover the flask with a piece of aluminum foil. We then heat the solution until it goes from a dark brown color, which is what it initially starts as, to a pale yellow, almost colorless or colorless solution. So again, we're going to go from a dark brown initially to a very, 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 very pale yellow, colorless solution. Then we're going to take that solution, pour it into a beaker, and then determine the mass of the unreacted zinc that's left in the Erlenmeyer flask. And this was determined to be or measured to be 0.48 grams. So now we want to calculate the formula of this product between zinc and iodine. Now the fact that there's unreacted zinc automatically tells you that all the iodine gets consumed. And the way we know all the iodine gets consumed is because it goes from a brown to a colorless solution. So when it goes colorless, that's a key indicator that, hey, this solution, all the iodine has been consumed. So we initially started with 1 gram of zinc. We started with 1.5 grams of iodine. We know the mass of the unreacted zinc. We can find the mass of the reacted zinc by taking the amount we started with and dividing or subtracting from it the mass of unreacted zinc. So now we have the mass of iodine and the mass of zinc. Remember when we did empirical formula, you need the mass of each element. Now we have the mass of each element. So again, it's under the assumption that all the iodine is used up. If all the iodine doesn't get used up, there's going to be an error in your experiment. So we find the moles of each element. And then what's next? So in empirical formula, mass of each element converted to moles of each element, and then divide by the smallest number. So here, zinc is the smaller number. So we get our ratio, it's 1 to 1.5. Again, 1.5, you cannot round to a whole number. So we need to get rid of the 1.5s. So we multiply by 2, we get a ratio of 3 to 2. So it's Zn2, I3. So there every 3 moles of iodine, there's 2 moles of zinc. Now, obviously, this is incorrect because we all know the formula of zinc iodide is ZnI2. So one thing you want to look out for, and this will help you in your analysis of the error, is when you're drying the product, keep your observations to note if you see any pink or purplish color in the product. And that will usually be an indication that you had leftover iodine in your product. And so that can be one of your reasons for the error. But these are the steps you go through to calculate the product of zinc and iodine. There's one more calculation we're going to do. We're going to calculate the percent difference. So we're going to take the mass of product minus the mass of the reactants divided by the mass of the reactants. So the mass of reacted zinc, the mass of reacted iodine. And so if we did this correct, our mass difference or percent difference should be 0, because the law of conservation of mass says whatever mass we start with, we have to end with. So here we have our mass of reactants. Once we dry the product, we get the mass of product. And here we have a percent difference of about 23.8%. And this is not surprising since our formula we calculated on the previous slide was incorrect as well. But this is how you calculate the percent difference. If you did everything correct, again, the mass of product should equal the mass of reactants. Your percent difference should be close to 0. So just a few experimental notes. Bear in mind that iodine can cause skin burns. It's also corrosive to metals. So when you weigh out iodine, make sure you use a weighing boat. We'll be using methanol. Methanol is flammable. It's also toxic, especially the vapors. This is, for those labs that are in the early morning or early mornings, you may want to make sure you have a full stomach, because sometimes everyone's in there trying to evaporate methanol. It can get kind of smelly. And so it's always good to have a little food on your stomach if you have an early morning lab. So one other key note is it's better to dissolve the iodine first in the methanol and then add the zinc to it. So that's also a good experimental note as well. So dissolve the iodine first, then add the zinc to the Erlenmeyer flask. So initially, when you start your experiment, just one thing here, they used a little bit too much aluminum foil. You don't need much, just right about here. But you see the initial color is a dark brown color. And you want to have it heated just the right heat to where you form a small amount of bubbles. Where the methanol heats up, it condenses, it comes back down. If you see very large, it's boiling very vigorously, you want to turn down the heat. You want a very gentle, slow heating, slow boiling of your solution. So after about 10 minutes, it's still dark brown. After about 40 minutes, it's still brown. Again, we're waiting for that colorless / very pale yellow solution. And after about 80 minutes, you see one of them has gone colorless. So what I'm trying to show you here is that this process takes a long time. And so you want to go ahead and get your reaction going, because it's going to take at least an hour to an hour and a half for you to get to that point of colorless. And you want it to be colorless because that way you know that all the iodine is consumed. So your starting solution is a dark brown. Your end solution is a colorless solution. So now I'm going to show you an actual walkthrough of doing this experiment. So here are two of the two reactants we're using. We're using 30 mesh zinc metal. And we're using iodine. So the first thing you want to do is you want to record the mass of 125 milliliter Erlenmeyer flask. So it's 99.2 grams. So let me write that here to the side. As such, I think it's 150 milliliter Erlenmeyer flask. That's why I was thinking. This is 99.2 grams. So it's very important you record the mass of the empty Erlenmeyer flask. Next, we're going to take the methanol and we're going to add methanol to the Erlenmeyer flask and then dissolve the iodine crystals. Now we're going to record or weigh out our iodine. We should weigh out 1 gram of iodine into the flask. So for my example, I weighed out 1.27 grams of iodine. So our mass of iodine is 1.27 grams. In your experiments, you'll be weighing out 1 gram of iodine. I'm going to pour the iodine into the methanol and mix it up. And make sure all the iodine has dissolved before you add the zinc to it. And so it's going to be a dark brown color initially. So the initial color, very dark brown color. So we measured out our iodine, we added to the Erlenmeyer flask. And now we're going to measure out the zinc mesh and add it to the flask as well. And just a disclaimer, when I'm showing you this, I use different masses than you would in the lab, just so you get some kind of different flavor of doing this. So that's just a disclaimer. So make sure you read the lab manual to know the actual masses of each reactant that you need. So here we're using 0.76 grams of zinc. So let's record that. So the mass of zinc, oops, mass of zinc, 0.76 grams. Now we're going to add it into the Erlenmeyer flask, kind of mix it a little bit, and then we're going to heat the flask. Next thing we want to do is cover the top of the flask with some aluminum foil. Like this. Again, you don't need too much. You just need to cover the tip or near the top of the flask. And again, you want to do this so that the methanol doesn't escape and you dry out your sample. So now we're going to heat the sample, and this is where it takes a long time for it to go from a dark brown to a colorless solution. You put it on the hot plate, and you want to get it to where it's heated to a gentle boil, so not too much. And so here you can kind of see it's at a gentle boil, and I have it set to around 155, but again, every hot plate is different. You want something like this where it's at a nice rolling boil as well. So again, this is time elapsed. So after, some time, I come back, I check it. It's still brown. After some more time, it starts to get to a lighter, like a golden yellow. So again, this is over the span of 20, 30, 40 minutes, an hour. So now it's starting to get almost done. It's still a little yellow pale. Again, we want it colorless, so that way we know that all the iodine has reacted. And so this takes a long time to do. So now we get to this point, it's colorless. You can kind of see if I make a note here, you can kind of see the unreacted zinc that's still at the bottom of the flask. And that's okay, because we're going to have some unreacted zinc left over. So now we want to pour this into a beaker, evaporate out the methanol, get our product. So what we need to do is we're going to pre-weigh the beaker. So we're going to get the mass of the beaker. So the mass of the beaker, 94.19 grams. And you're seeing while we're taking the mass of the Erlenmeyer flask, the mass of the beaker, because it's going to help us when we're recording the mass of unreacted zinc and the mass of product. Now we're going to take this beaker and we're going to pour the methanol solution into the beaker and then evaporate off the methanol and get our product. So here we are pouring the solution into the beaker. Now we use a glass stir rod to help prevent any spilling or splattering of the solution when we're pouring it. So we pour it along the stir rod. So that minimizes the splattering when pouring. And we're also going to wash with a little methanol the unreacted zinc to make sure we get all the product out. So we're going to add a little methanol to it. And you can do like, I think we're going to do 5 milliliters at a time. We kind of swirl it around and then we pour the solution into the beaker. And again, this is to help get out or remove any product that's still left in the Erlenmeyer flask. So you're going to do 3 washings of about 5 milliliters of methanol. She does 2. 2 to 3 washings. We want to make sure we get all the product out of the Erlenmeyer flask. Now, once we've done with the washing, we're going to put both things, both the Erlenmeyer flask and the beaker, on the hot plate. So in the Erlenmeyer flask is our unreacted zinc, in the beaker is the product in solution. So again, in the Erlenmeyer flask is the unreacted zinc. And in the beaker is the product in solution. So that's the difference between the two. Now we're going to put them on the hot plate and then dry out the unreacted zinc and evaporate off the methanol in the beaker. So here we're boiling off or evaporating off the methanol, and as you evaporate off the methanol, you get like a creamy off-white solid. Once it's done, then we're going to cool it down and record the mass of the product. And make sure you use beaker tongs if the beaker is still hot. So there's your product, kind of an off-white or creamy white color. That's the zinc and iodine product for your reaction. We dried the unreacted zinc in the oven. So now both the unreacted zinc and the product are dried. So we're going to record the mass of each. So the mass of the product and the beaker, 96.27. That's the mass of the zinc iodine product. And we're also going to get the mass of the Erlenmeyer flask and the unreacted zinc. Now we're going to get the mass of the unreacted zinc in the Erlenmeyer flask. Again, notice that the product, there's no pinkish or purple hue to it. So that means we got all the iodine out. So now we're getting the mass of the Erlenmeyer flask and the unreacted zinc. So about 99.65 grams. So very important, make sure you put the unreacted zinc into the solid waste container. We just pour it down in the Erlenmeyer flask. Pour the Erlenmeyer flask into the solid waste container. You can rinse it out with a little water and put that in the aqueous waste to clean your sample. But make sure you put the unreacted zinc and your product in the solid waste container. Only the solutions go into the glass jar. So only in the glass jar goes your solutions if you have any washings. And again, we scrape off the zinc iodide product. We're going to pour it into the solid waste, the plastic container. That's where the solid waste goes. And then when we're rinsing it, we're going to put the rinsings into the glass bottle. And that's how we dispose of the waste for this experiment. Again, I'm cleaning the beaker and then I'm pouring my washings into the glass bottle. So now let's take a look at these, the data we recorded, and let's see if we can calculate the formula of the zinc iodide product. Let's see how well our teaching assistants were. So the first thing we want to do is we want to calculate the mass of unreacted zinc. So again, that's going to be the mass of the Erlenmeyer flask and unreacted zinc minus the mass of the Erlenmeyer flask empty. So the mass of unreacted zinc is 0.43 grams. So the mass of reacted zinc is 0.76 minus 0.43. And that equals 0.33. So 0.33 grams is the mass of reacted zinc. Let's get our mass of product. Mass of product will be the mass of the product in beaker minus the mass of the empty beaker. And we get 2.08. So we have the mass of reacted zinc. We have the mass of iodine. We can calculate the formula of the zinc iodide product. We have the mass of product. We have the mass of the reactants. We can calculate the percent difference. So to calculate the empirical formula, we're going to need to find the moles of zinc and moles of iodide. For moles of zinc, we use the reactant, so 0.33 divided by, get my trusty periodic table, 65.4. And for moles of iodine, we're going to use the mass of iodine, 1.27, divided by its molar mass. Now we're only using the molar mass of I, not I2, because this is an empirical formula problem. 126.9. We get 0.00505. 0.0100. Oh. Now we're going to get the ratio. So for zinc, 0.0050 divided by 0.0050 is 1. For iodine, 0.0100 divided by 0.00505 get about 1.98, which is approximately 2. So our formula is ZnI2. Funny is the funny story is that our TAs thought we didn't do a good job, but yet when we put out the data shows us that we got the correct formula. So that's how you do your calculations. So let me just recheck everything and then we'll continue. So now to calculate the percent difference, we need the mass of reactants. And so the mass of reactants is the mass of reacted zinc plus the mass of iodine. And we get 1.60. Mass of product, 2.08. So our percent difference, 2.08 minus 1.6. Divided by 1.6 times 100. And so we have a 30% difference. One of the key culprits to this is that maybe our sample or product was still wet. So if we still had our product, we could put it back in the oven for a little longer, come back out, reweigh the product, and see if it uh, gives us better results. So since we had a high percent difference, the most obvious culprit in this is that it just wasn't in the oven long enough to dry the sample. And that could be the reason for such a high percent difference, because our formula is right on, but our percent difference is quite large. So that concludes uh, the video lecture for lab 3. And so in lab 3, we looked at empirical molecular formulas, how to do calculations for those types of uh, problems. Also, how do we apply the empirical formula to our particular lab and the calculations involved in our lab once we obtain the data. We also looked at those metals that react with water because they're highly active. Those metals, when we say react with water, they displace hydrogen from water. There are other metals that only displace hydrogen from steam. And then we looked at metals that displace hydrogen from acids. And then finally, we looked at the walkthrough of the process of performing the lab, and again, the calculations that you will need to do as well. So I hope this video lecture was informative for you. You learned something and you enjoyed the show. Always, if you have any comments, leave them in the comment section, or if you like it, just give me a thumbs up. It's always nice to know that people like my videos. So until next time, Dr. Armand signing off.